So now I want to actually look at how do we construct a proof and what is the logic that goes into coming up with a proof. So again, even if you don't end up writing a lot of proofs, you will end up reading a lot of proofs, right? So I think the best way to do this is just going through some examples of proofs. So we're going to start with what's called a direct proof, and then we'll look at different types of proofs like a proof by contradiction, for example, and another special type of proof called mathematical induction. So let's just start with proving this statement here. Okay, so this is we'll call it a statement. You can call it a theorem, a lemma, whatever you want to call it. So this says for all integers a, b, and c, with a not equal to 0, if a divides b and a divides c, then a divides b minus c. Okay, so we have like some qualifiers that we set up with, right? Which is that a, b, and c are integers. We have that a can't be 0. And then we get that a divides b and a divides c. And then we want to show that all of this leads to a dividing b minus c. Okay. So a key thing that we need to realize is that all of these qualifiers in here in the hypothesis, everything should be used in some way, maybe indirectly, but it all needs to be used. Otherwise it wouldn't be there, right? We typically want as little qualifiers as possible, because if we can take one in the mouth, then the statement is stronger. But if you're given a statement like this, it's probably there for a reason. So we want to use everything. So that's a good way to know if we're on the right track. Now, when you first look at this, you might not really even know where to begin. But we want to begin with what we're given, which is what's in our if statement here, which is that a divides b and a divides c. Okay, so let's go ahead. Let's just take that as it is, and let's see what we can come up with based on that, and see if we can start leading towards something that looks like this. Okay, so the right proof here. Okay, since a divides b, or maybe you just write, if you want to stick with the logic symbols, you could say a divides b implies that b is equal to a times some number, let's say k. Okay. If we're going to introduce this new number, we need to put a qualifier on it, which in this case would be that k is an integer. Okay. Just like our other numbers here, right? So they can be negative, right? A number can still divide a number if it's negative, right? We say -2 divides 4, for example, or -4. But a lot of times we're referring to the natural numbers here. But it's okay to work with the integers in this case. So b is equal to some a times k, okay? So that's what we get from that. And you might want to think, okay, why is this true, right? Why does this imply? And this is typically what you want to do with proofs, is think about why everything leads to everything else. And it might help to put in some numbers here, right? So we know like 2 divides 12, right? And that's because 12 is equal to 2 times 6, right? So it might help to think about it in a divisibility context instead. 12 is divisible by 2 means that 12 is equal to 2 times some number. So b is divisible by a means that b is equal to a times some number. Likewise, a divides c, right? So that's going to imply that c is equal to a times some different number k. So you can introduce another number. Maybe you want to put k1 on this one, just so you don't have to keep coming up with letters. But, realize that they are different things. Okay. So we have these two things. So now we have something to work with b minus c, right? Because we have b is equal to this, c is equal to this. So from that, now we can formulate what b minus c is. So b minus c is equal to ak1 minus ak2. Okay. So that's just reinserting the definitions that we just had. Now, by the distributive property, this is equal to a times k1 minus k2. And it doesn't hurt to, write down what your reason is for everything. You don't have to if it's something obvious, but, obvious means different things to different people, right? If you read proofs in advanced textbooks, they're going to skip a lot of things that you probably wish they didn't because they're not going to be obvious. But, so it's not a bad idea to just write down the steps, even if you might think they're obvious. So now we have, just to write it a little more cleanly, we have that b minus c is equal to a times k1 minus k2. Now, before we make a leap in logic to our conclusion here, we should say also k1 minus k2 is equal to some, say number k, which is an integer. Okay, so this is an important part of this too, which is that an integer minus an integer does give us an integer, right? This is a property of these sets of numbers, which is that they're closed under addition and therefore subtraction. So rational minus irrational gives you a rational, and so on and so forth. It doesn't work for irrational numbers, right? Like pi minus pi is 0, which is not irrational. But the natural numbers are closed under addition, but not subtraction. The integers are closed under addition and subtraction. Really, it's from addition, and they have additive inverses, which is what we call subtraction. But anyway, you could see just by trying out some numbers that if you subtract two integers, you will get an integer. Okay. So this means that b minus c is equal to a times k, and this was our definition of dividing, right, that we were using. So therefore, we have proven the original statement. So at the end of a proof, sometimes you see typed like a written square, a colored in square. Okay. Sometimes you see QED written. I don't remember what it stands for. It's Latin, which means and thus it says like something like and thus it is proven. My geometry teacher used to joke that that stood for quite easily done. Or you might, it might just be left blank. I think this symbol is what you're going to see typed most of the time, indicating that the proof is over. But, usually it's obvious the proof is over because they start talking about something else. Okay, so let's look at some more here. So this one says, for each natural number, or actually this is an integer. You're using n. N is typically used for natural numbers. Sometimes it's used for integers. If n is an odd integer, then n cubed is an odd integer. I know I said it before that, odd and even are typically only used for natural numbers, but I mean, it does come up with integers. I just think it's more common for it to be with natural numbers. Evidently, I was not thinking correctly though, because all these examples are using integers. But it just extends to the same definition where -1, -3, -5 would be odd, etc. Right. So it really comes down to different authors will define it different ways. But yeah, you can just forget what I said about it being natural numbers. It's used for integers as well. Obviously, as we can see here. So here we don't really have a lot to work with. I also just realized I didn't write this correctly. If n is an odd integer, then n cubed is not an integer. So this is another thing where, it might be kind of obvious if you just think about the numbers, but that's not good enough, right? We need to really define it for any number. So we're starting with the statement that n is an odd integer. So this is where that formulation of odd numbers comes into play, right? So we start with, okay, n is an odd integer. So n is equal to some 2k plus 1 or minus 1, it doesn't matter. And then you should put a qualifier on k, which is that k is an integer. Okay. Then n cubed is equal to 2k plus 1 cubed, right? So now we can just do some algebra and see what we end up with here. So I like to just square it first. There's formulas for cubing things, but I don't ever remember them off the top of my head. So we'll just square this first. So we get 4k squared plus 4k plus 1 times 2k plus 1. Okay. And then that's going to be 8k cubed plus 8k squared plus 2k plus 4k squared plus 4k plus 1. Okay. We could simplify this a little bit before moving on here. We can combine the 12k squareds. We can put in the 6k and then plus 1. So, well, how can we say that this is an odd number? Well, note what we can do here. We can get it back into this form of 2k plus 1 by saying, okay, this is 2 times 4k cubed plus 6k squared plus 3k plus 1, right? If we want to show it's odd, we need to show it's in this form. This is in that form, right? We do need to make the jump that this is an integer, but that's fine because integers are closed under multiplication and addition and all that. If you multiply two integers together, you're going to get another integer, right? I don't think that's something we need to really prove. So it's best practice to say that, note that 4k cubed plus 6k squared plus 3k is equal to some number m, which is an integer. Okay. So we have 2m plus 1, which is an odd integer. Okay. And then we're done. So now we've proven the original statement there.